So what we're going to discuss today, we're going to discuss how we can achieve microsecond latency with Java. Could we use Java for low latency systems? Is that possible or not? And what we did in order to make it possible. So we're going to speak about techniques, we're going to discuss how we managed to achieve something like that, and it's going to be an interesting journey. The things that we learned before, and all of the students learn about the good Java, it's not the things that is going to help us to build low latency Java. The things that we are going to discuss here probably is not the things that you are going to write, usually if you not take care about low latency. Okay, so there is one question. Is Java good for low latency or not? And we need to answer that at the end of this talk. So could we process more than 5 million operations per second? Is that possible? How we are going to achieve that? What kind of libraries, technologies exist at the moment, and if it's possible or not. The numbers that you can see on the screens and the number that we use, the number of the Exchange Core library, it's basically one very good library which we used a lot a couple of years ago when I was an architect, and one of my boss come to me and say, okay, we need to build crypto exchange. Okay, I say, we have a database, we have very good developers, so what was the problem? Then I spoke with the business guys. And one of our business guys go to me and say, we need to process 5 million operations per second. What? What do you mean with that? We need to be extra fast. Why? Why we need to be extra fast? Because there is a lot of market data that we need to process fast. And if you process the data fast, we're going to give the best price possible to our users. Okay, how we can do that? I don't know at that time. And when I don't know something, I do big research. So I was watching a lot of YouTube lectures, a lot of articles, and I found that library available on GitHub, and it's open source. And I basically started exploring that library. And we're going to do right now, we'll basically go over all the techniques that exist in that library and that I'm currently using on my daily basis. So first, we need to answer ourselves a couple of questions. How fast? What those really mean? 1 milliseconds, 1 microseconds, and 1 nanosecond. We need to know our latency. And basically, when we know our latency, we will understand how to build Java application. Who cares about the latency? So this is what we're going to handle right now. So we're targeting microseconds, not milli. We are targeting microseconds. Could we go faster than that? Probably yes. Is Java good? We can see. But we need to go as fast as possible, especially in the trading systems. But the question is, who cares about the latency? Who cares about the performance? Could we go without that? Probably. But there are specific domains who cares a lot. And one of the domains that I'm working on right now is basically trading domain, and we care a lot because we want to match fast. We want to process a lot of data. And one example, if the market is moving very fast these days, so there is a war, there is a lot of stuff happening in the market, and what's going to happen if we are not liquidating our clients at the exact time? Probably they're going to lose money, we're going to lose some money, so it's a big problem. Who else cares about that? Online gaming. So everybody who is playing gaming, it's care about latency as well. Real-time bidding. So how many of you are basically do sport betting? Somebody with sport betting? No? Okay. So you need to go fast. Is that all of the domains? Probably not. There could be other domains using that, but we need to be fast, at least in the trading. Who I am? So I'm currently engineering manager at Tradu. I'm not really engineering manager because I'm doing more software stuff instead of managing people. So I was around 10 years in the domain, most like fintech, gambling, distributed systems. I speak a lot about Kafka. Also, I'm a co-founder of small academy in my old town, Plovdiv. And I'm coming from Bulgaria. All the examples that you can see, the talk and everything, the benchmarks that we're going to discuss, you can find them in the GitHub, which is available over there. So you can go check, find, play yourself. All the examples, the slides are there. What this talk is and what is not. So we're going to discuss about mechanics of a receipt. I'm not going to tell you exactly how to build your systems. I'm going to describe techniques that you can use in your daily basis. So we're going to go over the different benchmarks that I run on my computer. So it's a little bit different when you run them in Mac or Linux, but you can see the real numbers. And the production validation. So in the beginning, I mentioned that there was a production validation, which is the library that is available on GitHub called Exchange Core. You can go and check it. What this talk is not about. It's not about Project Loom. So probably we're not going to speak about multi-threading. We're not going to speak about virtual threads. We're not going to speak about Valhalla or GraalVM. We're going to speak about native Java, pure Java, the Java that is available right now to us. The mental shift. If you remember at the beginning of the talk, I discussed that probably we're going to change our mind of using Java for low latency. So most of us are using immutable objects. We are thinking that they're best. We really like them. And basically, when I teach my students, so I tell you, use immutable objects, they're going to save your life, they're going to prevent production failures. But when I'm working on the trading systems, so we're reusing objects. Dependency injection. How many of you guys are using Spring? Okay. How many of you guys having dependency injections in Spring? Probably all of you. Okay, sounds good. But if you want to go with low latency approach, you need to use direct calls. So you don't need to refactor a lot. We're going to see a story that when you refactor something, things could become slower. Also, we need to go in the way without concurrency. So the concurrence hash map, it's wrong for us. We need to find a way how to not have multi-threading. And the question is one thread is good or not? We can see. Okay, so the next one, garbage collection. And we are Java developers. And we always do new something. And the garbage collection take everything else. So we usually don't care about the memory. But if you're doing low latency stuff, you start to care about objects. And the question is, could we go without creating so many new objects? Could we do something like that? It started feeling a little bit like C or C++, but this is the way how we are going to do that in Java. Okay, how the JVM actually runs your code? We need to answer that question in order to understand what we can do. So there was a couple of stuff. First of all, there is an interpreter, which basically collects the information about which line of code is called, how it's used. Then there is a C1. It's a fast compiler. Do kind of optimizations. Try to optimize the code if you see a lot of invocation of a particular method. What kind of optimization we can see? There is C2, which is a little bit more aggressive, because the code is already there. We have some information about the performance of the code, and we want to go fast. We want to analyze. And this is how the JIT really works. But if you look at that picture, so there was a couple of stuff that we need to understand here. So first of all, as you can see, there is a de-optimization as well. If something goes wrong, if the cache is not hit, we're doing de-optimization. And things start becoming slow. Also, we need to try to do our best to warm up our JVM. So if we're not warming up our system, probably in the beginning we can see a system that is very, very slow. And if you restart your exchange, if you're doing crypto exchange, and you start your exchange during market hours, there's no market hours in the crypto because it's 24/7, but you can see that things start slow in the beginning. This basically means you didn't warm up your JVM. Okay, what's it do actually does? So let's try to answer a couple of questions. How to optimize? Which object don't escape? So if there is an object created in only one method, and it's not returned by that method, could we do something in order to not create that object? Which virtual core are monolithic? Which loops are hot? Could we optimize something? And basically, it should do a lot for us. It's basically help us to go 10 times faster if we configure our JVM correctly. The cost of doing nothing. How many of you guys writing works like that? Are there any issues with that? Ignore that you can go something like that. Are there any issues here? Yes or no? What is the issue? Yes, exactly. So the problem is with that string. Every time when you cover that, it's basically create a new string for you. And this is a big problem. And also there is an invocation. Could we go fast? What we can do? We can wrap our work with if statement. And when the compiler go multiple times, it's basically going to remove that line. It's not going to be interpreted anymore. And basically we have zero location and it's fast. Okay, what else? What else we can do? So there is one funny story. Basically in the beginning, I was writing code. Now AI writing code for me, but I was pretty happy of doing refactoring. And I did refactoring a lot. If something don't like it, I just change it. I extracted one method. It was very big method, and I decided, okay, let's decide to cut some part of it. And then I deployed the system. It was under production. I was so happy. I did a great job. I was a good developer. But suddenly, my boss called me around 2 a.m. in the morning and tell me, the system is working very slow. I was, okay, but my code is amazing. It's beautiful. Everybody like it. What's happened? And the happen is that there was a trap. So before that, there was no invocation. And now I have invocation to my new method. And this is basically a problem that I faced at that time. So what I just did, basically revert the changes at 2 a.m. in the morning. So it was a funny story. But so when you're working in the space like that, you need to be very careful how you refactor your code and why. What you can do to see that particular trap that I mentioned in the beginning. So in JVM, there was a lot of flags that you can use. And the one of the flags that you're seeing here basically is going to provide you information which code is going to be inline in your method. What that really mean, actually? What the inlining really mean for us? It's basically take your code from the method invocation, get everything there, and put it inside your method. This is what inlining really mean. So if you add that flag, you're going to see exactly when your code is inline or not. You can change that. There is a parameter who can help you to change that. Do we need always to do it? That is another question. Everything in the low latency system, it's required to test it, benchmark it, to confirm that it's working or not working. What else we can do? Okay, every one of us is doing new something, new order, new marketplace update. But what happened? Every new create a bunch of metadata and a bunch of garbage that is going to be not required in next second. So if you're processing more than 10 gigabytes of data per second, what's going to happen? You're going to generate a lot of garbage. And what's going to happen after that? We have a garbage collection. What the garbage collection is going to do for us? It's going to stop the service, or it's going to slow down the service, which is a problem for us. So we need to basically decide what we can do in order to not create new objects. Could we do something like that? The next question is the memory wall. Where our data should live? There is a couple of levels. So the first one is inside the register. It's basically very close to the CPU. It's there. Then it's L1, L2, L3, RAM, or disk. So as you can see here, the difference between those and the latency, it's amazing. Look, now we have one cycle of the CPU if it's inside the register. When we move a little bit down, the latency increases dramatically. So if you need to go to the RAM, it's almost 100 times slower than L1. Okay, But we're Java developers. Why we care about that? Do we really need to care about that? If you're writing Java, if you're writing low latency Java, we need to start take care about that. Okay, so I speak about creation of objects, location of objects, but what really that mean? So if we need to divide the Java memory model, we can divide in the heap and not heap. So when we create the object, it's always going to the heap part of the model, and basically it's going to different generation, moving the data, depends of how old is data, if it's used, if not, could be garbage collected or not, and there is no heap. Where do our metadata live? The metadata is basically the information that every class, every object have. This is where the object is created, the pointer, some information that we usually don't care as Java developers. Information about the threads is also non-heap. Code cache, garbage collection, everything is living there. Okay, so we have two sides. We have heap and not heap. And we usually, as developers, we usually use heap. But if you're moving a little bit, you can see that the heap probably is not always the good answer for us. So the garbage collection is unpredictable. How many of you are watching Grafana dashboards with garbage collection cycles? Somebody? Okay. How many of you see exactly the same pattern every time? Only one? Are you sure? Okay, just joking. We are going to discuss right after that. But GC is unpredictable. You really don't know when it's going to happen. It's going to happen when you have a lot of customers, or it's going to happen when you don't have customers. So what's going to happen there? We need to understand that. Okay. What happened right now? We have a lot of garbage collection available on the market. We have G1, we have zero garbage collection, we have generation zero garbage collection. As you can see here, there is a different heap space in which they can work. So you can take, okay, we can just use zero garbage collection and our problem is solved. Is that really? I don't think so. So this could go for 1 millisecond. If 1 millisecond is slow, yeah, definitely. For 1 millisecond, the price could be changed multiple times, and basically we can lose money. Losing money is not good, at least for me. So losing money is not a good idea, probably for all of you. But 1 millisecond is still not enough. Okay. Let's discuss about 2-to-1. Off-heap beats on-heap. What does that really mean? We need to be able to create our objects which is not in the heap. They should be off-heap. How we can do that? We can do that with a snippet like that. So you have a byte buffer, you allocate some memory on the start, and that memory is off-heap memory. After that, you can create the usable buffer, and you can write the data inside the buffer. There is no new here. As you can look, there is offset and putting the data and fetching the data. There is no new, there is no allocation. Everything is living out of heap, which is amazing. What that give to us? What we win? No allocation on hot path. What really hot path mean for me? The hot path is basically my matching engine, my risk management system, the things that it's responsible for monitoring money of the people. So this is my hot path. There is no allocation. If there is no allocation, there is no garbage collection. There is no object in the headers. There is no copy. We're not copying data between different parts of the method. So everything is kind of fast. And let's return back. We're using only primitives. There is no wrappers. Wonk, double, int. That is different story how you're going to store the amount. So the price shouldn't be a double if you're writing a trading system, but that is different story. We're not going to discuss that right now. Off-heap versus on-heap, the numbers. You can see the numbers, how fast we can go if you're using off-heap. And because there is no allocation, there is no garbage collection, we have a predictable memory. we know exactly how our garbage collection is going to behave, and we are happy for that. Yes, one win for us. No new, it's good. What else we can do? Do we really need to do off-heap always? Probably no. If you're creating a CRUD operation, or some operation that you really don't need to care about the performance, probably you can do it. So if you're using Kafka or technologies like that, yeah, you're going to create a lot of heap data. But when the things start to become a little bit different, and you try to cut your milliseconds, then you need to start thinking about the off-heap. Okay, the next question that we need to ask ourselves, is single-threaded beats multi-threaded applications? Okay, raise your hand if you think the multi-threaded application is better than single-threaded. Somebody? Multi-threading? No, why? How many of you are using multi-threading applications on your daily basis? Okay, and why you don't think that it's good? Probably, it should be, at least in some points. But if you're writing low-latency applications, single-threaded is better for us. There is no walks. Okay, what we can do instead? We can shard our data and basically assign a particular portion of our data to the particular thread. This basically means that only that thread is going to have access to that data. We are not locking everything. We are just using sharding, and we are sharding per thread. Why? Why we are doing that? No synchronization, no concurrency. Everything stay close to the CPU. We are not going every time to the RAM. We are trying to keep the data in the cache, in the CPU cache. Okay, sounds good. Sounds we have one more win. Let's see what else we can do. Sharded was content, the numbers. Okay, I personally really like the libraries like Disruptor and Agrona, so I'm a big fan of them. I use them on daily basis, so we're going to see what those libraries is doing, but basically, if you use them, you can call fast. Okay. Why walks are expensive? So the walks are not really expensive. They're expensive what happened behind the scenes. So if there is when you walk something, the cache lines are restored. So the data is not in your CPU anymore. It's somewhere else. So if you return back, if you go to the RAM, it's slower. Okay, kernel transitions basically mean that you park your operation level thread for something else. It's cost you microseconds by just using synchronize. For sharing, if there is two items in the same cache and they are not related, if you touch one of the items, the entire cache is invalidated. So that it works. You can see there's a couple of benchmarks. You can go and check in the GitHub repository how we are going to test that and basically prove what I'm saying. Okay, the next problem. Pools beats allocation. Could we create just one pool of objects and reuse them? Okay, we're doing the same for Hikari pools. We're creating a bunch of connections and we're reusing them. Why we're doing that? Because we don't want to create a new connection to the external service every time. This basically costs network traffic, establishing connection. There is a lot of stuff happening behind the scenes. Could we do the same for just objects in our application? Probably, we can do that. But why we want to do that? Imagine you need to process a lot of operations per second. Let's imagine you want to process 5 million operations per second on the single application. And the data is moving. It's very fast. You're creating new objects, new objects, new objects. And at the end, you're going to end with a lot of garbage. And the pools could help us with that. Before we're moving to explaining what the pools are and how we are going to implement them, let's look at that. It's something very simple. It's basically ring buffer. The idea of that, it's just an array with 2 pointers. The one pointer is pointing from where you read the data, and the next one is pointing from where you write the data. And it's going to provide you a very easy way to read and write asynchronous. When I say asynchronous, doesn't really mean more threads. It means 2 threads could go in each direction and taking the data without touching them each other. So there is no synchronization, which is good. How we are going to create a pool of objects? This is just an example how you can do something like that. You can go do ring buffer object pool, create an object. We are using generics. We are writing good Java, new Java. It's not Java 7. And we are doing that for us. It looks pretty good. So we are pre-allocating the entire data in the beginning. When our app is starting up, we are just getting that data for us. We are not doing allocation when our application is working. We are doing that on the startup, which is good. Okay, pooling versus allocation, the real numbers. If you're doing that, if you try to allocate just million times a particular object, you are going to end with the numbers like that, which is bad. If you create the pool of objects before that, yeah, you reserve that data for the entire time. So in the trading, CPU in memory, you can think that it's free resources. So you can request as much as you want, and they're going to give to you because you need to be fast. You allocate the data before it's required. And this is where the things change. Because you already have that allocation, you're not doing it, you're using objects. Okay, what else you can do? How many of you are using something like that? You're not creating a new instance of true or false or 0. How many of you are using something like that? In your code? Okay, why are you doing that? What was the reason? Could I just say new Boolean and paste to there? Could I do something like that? Yes or no? Yeah? But why were we not doing that? What was the reason? Yeah, somebody? Yeah. Because it's created only once, and we're using that for us. The next question is lazy initialization. Let's see if I have examples with those, because it's going to good. Could we create the canonical objects, not only with just those 2, can we create it as usual, and how we can do that? Let me see where was my... I hope it's somewhere there. Okay, let's zoom a little bit. How we can achieve something like that? Okay, we can create one weak hash map. We create in the beginning, then we are inserting the value only once. And if there is still reference to that data, we are going to reuse the same object. When the references just disappear and there is no reference to data, weak hash map is going to delete that object for us. But we have just one reference for the entire time if you're using it. If you're not using it, it just disappears, which is good. Okay, lazy initialization. Usually in my code, if I'm not writing for my company, I'm always doing something like that. Get calendar, get instance, data format, get instance, and things like that. I'm usually doing something like that, always. And as you can see, doing something like that, every time it's cost for us, because it's going to require to go to the instance, then there were some checks, there was a checking, get default. This is doing a lot of operations for us. And we need to do it only once when it's required and reuse it. And this is basically thread local. Yeah, I'm not a big fan of thread local, but you can use thread local to save your simple data format, number format, and reuse those objects for the entire process, which is good. And as mentioned in the beginning, we're going to do a code which is single-threaded. So there is no issue. We can still reuse that. We are happy. OK. Don't reinvent those. So we discussed about patterns, but do we really need to start implementing those patterns by ourselves? I wish to do that, but if I need to go to my boss and tell, OK, I'm going to need around a week or two to implement those patterns, my boss is going to just kick me off of the company and hire somebody else. And that was the reason why there's a lot of libraries that we can use for the same stuff. And let's go with some of them. One of my favorite libraries, it's called LMAX Disruptor. So it's basically the implementation of the ring buffer that we already discussed. So it's provide me weight strategies. It's give me possibility to assign a thread to the particular CPU, which we are going to see in a second. It's going to give me possibility to have multi-producers and multi-consumers. Also, it's going to tell me that there is no allocation, which is great. Is it easy to use a library like that, which is walk-free? Probably. Let's see how easy that could be. Again, let's try to find an example. It should be somewhere here. I hope. No. OK, it's here. Let's zoom, move that. How are we doing that? So we decide the buffer size. Probably the number is not just random. All of you probably know why it's something like that. It's power of 2. But we decided about the buffer size. Then, what we're doing? We're saying, new disruptor, what we're going to do, how our object putting is going to create it, with which object is going to create wonk event, which basically just value and setter. Then the buffer size, and how you're going to create the threads. And I am basically set instance. What that's going to do, we are going to discuss. It's basically a simple way of creating threads. Is that good or not? We are going to see. But this is how you can use the disruptor. Then, OK, I'm creating that disruptor. What I can do with it? I can add different handlers. And I can add the handlers which handle something specifically for me. So I can add a handler who is handling my market orders. I can add a handler who handle my risk data. I can change, I can basically add them in the chain and chain them, which is good. So I can add as much as possible handlers. Then I can just call start. And because I'm giving here a thread, it's going to start the disruptor in the different thread. Then I'm getting the ring buffer and start publishing events inside the ring buffer. And this is how easy it is. Basically, the entire Exchange core is built because of the disruptor. And everything there is with disruptor and that chain of events, which is good. OK, let's move. There was a very interesting article about the disruptor versus array blocking queue. The first time when I read that article, I was, OK, why? Then I did some kind of benchmarks and to understand that the disruptor is very fast because there was a busy spin, zero location, single-digit nanoseconds for hands-off between those handlers. It's very fast. OK, what else? Is that the only library that we can use? No. There is many other libraries. The one that I'm really not a big fan of it, right now at least, but before in one of my previous companies I really enjoy it, it's called canonical queue. You can create a queue in your machine which work with memory mapped file. So it's basically storing the data in your disk as a memory mapped file. There is no garbage collection, and basically handles sub-milliseconds latency for interacting with it, which is pretty fast. So if I need to implement something right now, and it's going to work in the same host, probably I'm going to use canonical queue for that. I'm not going to use Kafka because everything on one host and using Kafka to communicate between services which it's living together not makes sense. So the canonical queue is a good approach for doing that. Let's see if I have a demo with it. Okay. I have two applications. The first one, it's basically reading the data from my console and basically send that to the queue. And the next one, it's basically reading the data from the queue and put that in the inside my console. Let's try to run it. I hope it's gonna work this time. Okay, this one is up. I need to restart this one. Okay. Okay, let's see. As you can see, the data is arrived almost right now. And everything is written in the disk. So if I restart one of the services, it's going to restart from where it's ended, and then I can reread the messages. It's very fast. Okay, let's shut down those parts and move. Oh, canonical queue was Kafka, so there is no comparison. With Kafka, you need to go to the broker. There is a network hop. If the Kafka is deployed in your local machine, there is still hop because it's going to network adapter in your machine, then return back to the Kafka. Kafka needs to send the sync. There was some batching, so it's not a good idea. Okay, what else we can do? So most of us are implementing a currency hash map for local caches, which works pretty good if you don't need to care about latency. But there is another way. You can use canonical map and basically store your caches outside of heap, which is very good. You can handle a million of entities without garbage collection, without garbage pressure. And eventually you can store that to the disk as well if you want. I'm currently building my gateways with canonical map. It's working amazing. So I'm storing the data for my customers in the gateways in order to use them fast before they're reaching my ARM cluster. But it's very good. So I'm using that to keep my data locally to my gateways, and basically when I restart them to get the fresh state. Okay, what else? Could you use something else? Yes, we can. There was a library called Agrona. How I learned about it, that was a very interesting story. So it was during the night, as usual. And my boss came to us and say, okay, you have 3 weeks to build a crypto exchange. And me and my colleague was, how many weeks? Only 3 weeks. It should be ready. Okay? And the funny part is the engineering manager at that time just say, okay, it's going to be ready for 3 weeks. Okay, so usually at that time, I open a bottle of whiskey and drink a lot. Just to realize what my boss is telling to us, that we need to build a crypto exchange for 3 weeks. And to a situation, how that should be possible. We tried to experiment during the entire night, and around 10 a.m. in the morning, we basically realized that we really don't know how to deal with those libraries, how to deal with hash maps, how to deal with hash set, how we're going to handle the situation with boxing and unboxing, what that really do for us, how we're going to handle it. And we found that library, and basically we didn't succeed for 2 weeks. We built a first version for around 1 quarter and a half, but it's very different story because when you don't know, you should say, you don't know, I don't know. Let's try to investigate. And this is how we found the Agrona library. Okay, is Agrona fast? Yes, it's around 7 times faster than HashMap because of unboxing. You don't have unboxing. You are storing int as int, not as integer, which is good. And as we discussed, a grammar ring buffer is faster than array blocking queue already. Okay, what we can do with the CPU? We can buy very big machines with a lot of CPU resources, but we need to find a way to use it correctly. The first problem is false sharing. So we need to find a way how our data to be co-located in the same level of cache. And we can do that. We can add padding. We can use content. So there is a way how you can structure your code in order to be more easy for the CPU to use. This is one of the things that you need to do. If you don't doing that, probably the different threads is going to take the information, is going to clean the cache, and you have a problem. Okay, then batch prediction. Is there a guarantee that sorted array and unsorted array is going to behave in different way from the code snippet here? That was a question. And usually I would say, no, they should behave in the same way. Most of my students say, okay, they looks pretty the same. You have a if, then you have a sum. The code should do the same. But in reality, the sorted array is faster, at least 3 times faster than unsorted array, because of branch prediction. The GVM know when it's sorted array that the first couple of elements, which it's here, are going to skip, and then it's going to start processing after that. But it's not known without that, so need to check every element. There is no way to do a branch prediction. Okay, then, is there a way to assign a thread to the particular CPU? Yes. There's a couple of different ways how you can do that. You can use Linux settings, as this one here, in which you can assign a thread to the CPU and the process to the CPU. But is there a way how I can do that from the Java? Yes. There is a way. There was a library who can help you to do that. And let's see the example. How we can do that. Okay. Let's make it a little bit bigger. So first of all, we are going to get all variables processed to my Mac. It's old Mac, shouldn't be so much. Then we can say affinity acquire core. This basically gonna do something like that. For this particular thread, only one core is responsible for. And that core is reserved only for me, only for my thread. So I can do a thread affinity here. Then, when I'm starting a new thread, I can say, okay, give me another core and assign that core to me, only to me, which is good. Then I have 2 threads assigned to 2 cores, and nobody is going to pick that core. So only my threads. I'm assuming when nobody's touching those cores, their cache are only for me, and I know how to use them. So I'm assuming that I'm fast. And let's see. Let's try to zoom that. How to zoom? What is interesting story? Yeah. Look, so main thread is assigned to that particular CPU. The worker thread is assigned to the next one. But the interesting part that only those 2 threads are always assigned to the same CPU because we did a thread affinity. And how we're doing that? Actually, we're using a library called OpenHFT affinity, which is good. So there is a library for almost everything, and we don't need to reinvent the hot water. Okay, what else? We can do escape analysis. We can do walk-free. We can choose the better garbage collection for us, and we do our magic. So the next question is, how does sub 10 millisecond system actually look like? It's not how it looks like in my current system, but it looks something like that. You get a quant order, there was a LMAX disruptor, there was a ring buffer, and you have multiple threads which is assigned to the particular CPUs which do busy spinning. Basically, the threads are not stopped. They're always trying to get the information. So usually if you have alarms about the thread use, the CPU use, you can see that those threads are running on the max power to get the data. And I'm processing the information, and I'm persisting that information to the disk, which is good. This is how typical system looks like, and this is basically how the exchange code work behind the scenes, which is amazing. And it works pretty nice. What was the problem at that time when we implementing something like that with the exchange core? The problem was not the exchange core. The problem was the software that we built around it. So at that time, we used Kafka. So that is not good technologies for low latency, but we managed to go around 1 million requests per second with Kafka, which is good. We pay a lot of the Kafka, but we managed to achieve it. What else we didn't manage to do? Because we run in the Kubernetes it's not so easy to do a thread pinning. At least for 5 years, I'm searching for a solution and still don't know how to do it. If somebody knows, please tell me. I'm going to give a beer after the talk. So if you know how to do thread pinning in the Kubernetes, give me a beer. I'm going to give you a beer. Give me a solution. Not one, more than one. Okay. And all of those techniques together help us to do low latency with Java. Go off heap, sharding, pooling, assigning a CPU to the thread. Okay, so couple of resources. There was a bunch of resources available at the moment. This is the link to the GitHub repository, which contains all the examples. This is a link to the Exchange Core, which I used a lot, Agrona, LMAX distributor, Canonical Q, and OpenHFT for thread affinity. And some other articles. So Java Performance Second Edition is very good. Mechanical syntax block as well. And basically, that's it for me. Thank you, guys.